Hi, in this video, we're going to talk about work. When we say work, what's the first thing that comes to our mind? We use the term work in everyday conversation to mean many different things. We talk about going to work, doing homework, and working in class. But physicists mean something very specific when they talk about work. In physics, we use the term work to describe the process of transferring energy from object or system to another or converting energy from one form to another. In this picture, we see a girl pushing the cart. The girl is releasing energy to push the cart. That means the girl is doing work. We are going to explore this definition and how it connects to one of the most important principles in physics, conservation of energy, and we will also learn what physicists mean when they talk about another concept that comes up a lot in our daily life, power. So now, let's go to work. Work is calculated by multiplying the force by the amount of movement of an object or its displacement. Work is equals to force times displacement. Let's say if you have a box and if you apply force to the box in the x direction and its displacement, the work will be positive. And if the displacement is moving towards the left side of the x-axis, and we apply force in the right, then the work would be negative. So if work is positive, the kinetic energy decreases and the object speeds up. And if the work is negative, the kinetic energy increases and the object slows down. Now let's move on to circular motion. Let's put it this way. We have Earth here and Moon. The Moon is in orbit around the Earth. Now, the Earth exerts a gravitational force on the Moon that accelerates it towards the Earth. The Moon is moving in this direction and it has a displacement in the positive y direction. But the Moon is gonna turn instead to straight up to remain in orbit to the Earth. Now, the force and displacement are perpendicular, so no work is done. In fact, work is equals to force times displacement times cosine theta. So the angle theta is 90 and cosine 90 is equals to 0. So since gravity does no work on the moon's gonna do orbit. So now let's have some exercises about work. So here's question number 1. How much work is done by the horizontal force of 150 Newton that acts on a crate for a distance of 10 meters? So work is equals to force times displacement. Our force is 150 Newton times 10 meters equals to 1,500 joules. we use joules as the unit for work. In letter B, this is letter A, how much work is done on the crate across a frictionless surface? If there's no friction, the work done on the crate is gonna be 1,500 joules because the crate is going to receive the 1,500 joules that was transferred to it by the force. So the work is still 1,500 joules. Question letter C. How much work is done on the crate if the crate returns to rest due to friction? So, we have a force of 150 Newton. Work done is 1,500 joules. Now, if the crate goes to rest, that means there's a frictional force that's acting on it. Friction tends to slow things down, and so the energy that was transferred by the force was eventually transferred to friction because friction brought it back down to rest. So the work here, work of friction, is equal to negative 1,500 joules. So our net work is equal to work plus friction work. So we have 1,500 joules plus negative 1,500 joules is equal to 0. Now let's move on to our second question. So the question is, a 40 kilogram box is pulled 100 meters by a tension force of 200 Newton at 30 degrees above the horizontal to the right. A constant kinetic frictional force of 80 Newton impedes the motion of the box. Let's draw it this way. We have a 40 kilogram box tension of 200 Newton and 30 degrees above the horizontal. We have 80 Newton here. Now, the tension force has an x exponent. Tx. So Tx is parallel to the box. So the work done by the tension force is equals to Tx times, because these two, the box and the x component of the tension, are parallel, then the angle between them is 0 and cosine 0 is 1. So that work of tension is equals to T cosine 0 times displacement. Now the angle between T and the displacement is 30. So we put it this way. The tension is 200 times 1 because cosine 0 is 1. So 200 times 100, the displacement, times the cosine 30 equals to 200 times 100 times the answer is 17,320.5 joules. In question B, how much work is done by friction? So work, friction is equals to Fr times the displacement. So because our frictional force in here is going to the left, that means it's negative. So negative 80 Newton times the displacement of 100 meter is equals to negative 8,000 joules. And in question letter C, calculate the net work done by the box. So net work is equals to work done by tension plus the work done by the friction is equal to 17,320.5 joules plus negative 8,000 joules is equal to 9,320.5 joules. So that is all for work. I hope you've learned a lot about it.
In the previous video, we have learned work. So now, let's learn about energy. So, what is energy? Energy in physics is the capacity for doing work. It may exist in potential, kinetic, thermal, electrical, nuclear, or other forms of energy. There are moreover heat and work. Example in energy in the process of transfer from one body to another. After it has been transferred, energy is always designated according to its nature. Hence, heat transferred may become thermal energy, while work done may manifest itself in the form of mechanical energy. Energy can be neither created nor destroyed, but only changed from one form to another. This principle is known as the conservation of energy, or the first law of thermodynamics. So, let's watch a short clip about the conservation of energy.
Laws of conservation of energy. We now know that the form of energy can be changed from one form to another. Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor be destroyed. The total energy before and after the transformation remains the same. Let us consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be 1 upon 2 mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h is equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy is equal to constant, or mgh plus 1 upon 2 mv square is equal to constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. There is thus a continual transformation of gravitational potential energy into kinetic energy.
In the International System of Units, or SI, energy is measured in joules. 1 joule is equals to the work done by a 1 Newton force acting over a 1 meter distance. So joules is equals to 1 Newton meter acting upon over 1 meter distance. So there are two main types of energy, kinetic energy and the potential energy. So first, the kinetic energy. Kinetic energy is the energy by virtue of its motion. And the formula for kinetic energy is 1/2 mv squared. Another type of energy is the potential energy. Where the energy is at rest. The formula for the potential energy is mass times gravity times height. So let's have some exercises. So our first problem is energy of 4,900 joules used to raise an object with mass of 50 kilograms to a height of h. So what is the height of h? Acceleration due to gravity is 9.8 meter per second squared. So given is the change of potential energy equals to 4,900 joules. The mass is equals to 50 kilograms. And acceleration due to gravity is equals to 9.8 meter per second squared. So let's find the height. So the solution is change in P is equals to mass times gravity times change in height. So the change in potential energy is 4,900 joules is equals to 50 kilograms times gravity of 9.8 meter per second squared times the height, which is unknown. So 4,900 is equals to 50,000 times 9.8 meter per second squared is equals to 490 times change in height. So change in height is equals to 10 meters. So let's proceed to question number 2. Suppose a car has 3,000 joules of kinetic energy. What will be its kinetic energy if the speed is doubled? And what if the speed is tripled? We already proved in kinetic energy lesson that whenever the speed is doubled, the kinetic energy is quadrupled or 4 times as big. So 4 times 3,000 is equals to 12,000 joules. Therefore, the kinetic energy is going to be 12,000 joules. So let B be the speed of a moving object, that speed is equals to 3v after the speed is tripled. So k is equals to mass over 3. The 9 that you see means the kinetic energy is multiplied by 9. So 9 times 3,000 is equals to 27,000 joules. So therefore, the kinetic energy is going to be 27,000 joules. So there you go. I hope you have learned a lot in this video.
So in the last video, we have discussed about work and energy. Now, let's discuss about power. Power is the rate at which work is done or energy is transferred in a unit of time. Power is increased if work is done faster or energy is transferred in less time. The equation for power is P is equals to W over T, wherein P is equals for power, W is equals for the amount of work done or energy expended, and T, which stands for the amount of time. In calculus terms, power is a derivative of work with respect to time. If work is done faster, the power is higher. And if work is done slower, the power would be smaller. Since work is force times displacement and velocity is displacement over time, we can say that power is equals to force times velocity. More power is seen when the system is both strong in force and fast in velocity. Power is measured in energy divided by time. The SI unit of power is the watt or joules per second. Power is a scalar quantity. It has no direction. Horsepower is often used to describe the power delivered by a machine. Horsepower is a unit of power in the British system of measurement. It is the power required to lift 550 pounds by 1 foot in 1 second. It is the power required to lift 550 pounds by 1 foot in 1 second and is about 746 watts. The watt is often seen in relation to light bulbs. In this power rating, it is the rate at which the bulb converts electrical energy into light and heat. A bulb with a higher wattage will use more electricity per unit of time. If you know the power of a system, you can find the amount of work that will be produced as W is equals to PT. If a bulb has a power rating of 50 watts, it will produce 50 joules per second. In an hour, which is converted to 3,600 seconds, it will produce 180,000 joules. When you walk a mile, your motive force is displacing your body, which is measured as the work done. When you run the same mile, you are doing the same amount of work but in less time. The runner has a higher power rating than the walker, putting out more watts. A car with 80 horsepower can produce faster acceleration than a car with 40 horsepower. In the end, both cars are going 60 miles per hour, but the 80 horsepower engine can reach that speed faster. In the race between the tortoise and the hare had more power and accelerated faster, but the tortoise did the same work and covered the same distance in a much longer time. The tortoise showed less power. When discussing power, people are usually referring to average power. Or P average. It is the amount of work done in a period of time, or the amount of energy transferred in a period of time. So this is the amount of work done in a period of time, which is the change in work divided by time, and this is for the amount of energy transferred in a period of time, which is the change in energy over time. So let's move on to answer some exercises. Let's start with number 1, which is a 20 kilogram crate is lifted 200 meters above the ground in 5 minutes. A. How much work is required to lift it 200 meters into the air? B. What is the average power exerted on the crate? Let's first get letter A, which is the required work to lift it 200 meters into the air. So, work can be equal to the change in potential energy, which is mass times gravity times change in height, which is equal to the mass, which is 20 kilograms, the gravitational acceleration, which is 9.8 meter per second squared, and the height of 200 meters. Now, the energy required would be 39,200 joules. After getting the work, we need to then get the power, but first, we need to convert the 5 minutes into seconds. Now, 5 minutes into seconds will be equal to 300 seconds. After getting the time into seconds, we can then get the power, which is work over time. Now, let's just substitute the work, which is 39,200 joules, and the time, which is 300 seconds, which will give us an answer of 130.7 joules per second, or 130.7 watts. A horizontal force is used to accelerate a 15 kilogram block from a speed of 20 meters per second to 40 meters per second in 10 seconds. A. Calculate the magnitude of the force applied. B. What is the average power exerted on the block? C. What is the maximum power exerted on it? So, in letter A, we need to get the force, which is equal to mass times acceleration. But we don't have the given for acceleration, so we need to find it first. But before that, let's make first a graphical representation of the problem. So here is the 15 kilogram block, at 20 meters per second. We then applied force, and after 10 seconds, it have a 40 meter per second velocity. So with a given final and initial velocity, we can get acceleration through a certain kinematic equation, which is v final minus v initial is equals to at. Now we have the time, so we need to divide it by time to get the acceleration. And therefore we should plot the final velocity minus the initial velocity and divide it by time, which will result as 2 meters per second squared as our acceleration. Now, after getting the acceleration, now we can get the force by plotting the mass, which is 15 kilograms and 2 meters per second squared. Now, we will have a force of 30 newtons. Now, moving on to letter B, which is what is the average power exerted on the block, means we will find for the average power, which is work over time. Now, in order to find work can be equal to force times distance. Force times distance over time. Now, we can see this as equal to velocity, which means that power is equals to force times velocity. Now, with a given equation, we need to find velocity. But since our speed is not constant, we need to get the average speed. In order to get the average speed, we have to add the initial and add the final velocity and divide it by 2, which is 40 meters per second plus 20 meters per second over 2. And then we can get the velocity average of 30 meters per second. Now that we have the average velocity, let's substitute the values to get our average power. So 30 newtons multiplied by our velocity, which is 30 meters per second, would be equal to 900 watts. So let's go to letter C, which is what is the maximum power exerted on it. In finding the maximum power, we need to multiply the force to the maximum velocity, which is, our force is 30 newtons, and the maximum velocity based on the problem is 40 meters per second, which will give out an answer of 1,200 watts. Now, this would be the same for the minimum power by multiplying the force to the minimum velocity of the object. Minimum power is equals to force times V minimum, which is 30 newtons, and the minimum velocity of 20 meters per second, which is equal to 600 watts. I hope you learned through this discussion about power.